Okay. Hello. Welcome to our RAS seminar. Today we have Guido Araujo presenting the architecture is dead, long live the architecture. Go ahead, Guido.
Okay, thanks for the nice introduction, Marcio. One interesting that we have recently witnessed is news that the architecture is dying because mostly we cannot manage to have more useful transistors in silicon die. But as a matter of fact, the news about the death of the architecture are hardly exaggerated. In fact, we're starting a new phase in computer architecture, which has been called the phase of the accelerators. And my goal of this talk is to convince you that this era is starting and how it's gonna look like. Okay, I'm not sure if most of you are familiar with that, but in this past November 2021, we celebrated the 50th anniversary of the first microprocessor. First microprocessor was the 4004 4-bit processor, which was designed by Intel, and we completed half a century of its design this past year. And jumping from that 50 years forward, we have 2022, we have a very, very interesting technology, powerful technology. We have managed to put lots of multi-core architectures working. We have tons of cores, Intel processors. IBM with their power technology also has that. We can have on the embedded front a number of very interesting and low power designs with quad-core and 8-core ARM processors. And recently we have this reconfigurable technology, which is put forward by Sci5 and other companies using the RISC-V technology. And not to mention also the AMD multi-core processors. Okay, so 50 years from the beginning of the first processor, the first microprocessor was released 50 years ago, we now have this wonderful, great technology. But things were not that wonderful on this path. For example, around 2000, early 2000, we had this interest talk by Pat Gelsinger, the Intel CEO, about the problems we're facing about power consumption on microprocessors. So from 1971, when the 4004 was released, to around 2000, most of the processors, if not all of them, were below 10 watts per square centimeter. In other words, we had like around 5 watts per square centimeter in power dissipation in the 880, one of the first 8-bit processors. And these things kept evolving for some time, roughly around 30 years without any major increase in power consumption. But the point is that Moore's law allowed us to put more and more transistors into a small die area. And around 1998, during the Design Automation Conference, Pat Gelsinger put this slide, which was a major turning point on this area. What happened is that we broke the barrier of 10 watts per square centimeter in that year. And the previsions, not the forecast that Intel was doing for the future processor were like that. Around early 2005, we would have like a large increase in the power consumption. And this would keep progressing. And until 2010, we would have like the density, energy and power density of our nuclear reactor, a rocket nozzle, and then the sun surface. Of course, this would not happen because we would burn the die by then. So in order to control that, some decision had to make in terms of technology. We would continue to put more and more transistors into die, but we could not clock them with the same speed because, of course, as we all know, the power consumption of a microprocessor depends strongly on the frequency that operates. Okay, but on the other hand, we had Moore's law continue in full steam. By 2000, we still have this nice feature that the number of transistors would duplicate every 2 years. And that continued beyond 2000. And okay, so we had this ability to put more and more transistors, and the Moore's law continue working, but we could not handle the power density that would result for that. So what would we do? We can put more transistors, but we cannot clock them with the same speed. The point at that point, it was clear to the industry that the solution was to use multi-core processors, because we could still use all those very large number of transistors, but since we could not clock them at the same speed, in other words, we could not put all those transistors to work in a single processor, we could at least break them in small processors and have them clock in a smaller clock rate. So the overall message here is we will not be able to put those billion transistors to work in a very high speed, 16 gigahertz, for example, clock rate, because this will lead to a high watts per square centimeter density. But on the other hand, we could have, like, for example, for the same area, 16 cores working at a smaller clock rate, like say 4 gigahertz, with a very good relation of watts per square centimeter, or at least a power density that could be handled by traditional cooling. So this, of course, led us to the multicore area, right? But there were some problems with this decision that we realized later. We're talking about the year 2000, okay? So we're talking about the year where Power 4 architecture, a dual-core Power 4 architecture was released by IBM, and this was the first processor for the multi-core area. And from that point on, everything worked kind of as anticipated, right? We continue to be able to push more and more transistors into a die. We start seeing a saturation in the single track performance, of course, because for a single thread, it would run in a single processor, and the process could not run with the same clock speed. The clock speed, of course, saturated for the reason just mentioned. The power, of course, saturated because now we're measuring the power for a bunch of small cores which were clocked in a smaller frequency. And the number of cores, increased. So that year marked with the IBM dual core Power 4 marked the beginning of the multi-core area. But this was good from the hardware folks, right? Because they said, okay, now we have delivered for close to 30 years, a doubling in clock rate for you software folks. And well, we cannot do that anymore. We have designed this nice multi-core technology. Now you software folks have all these multi-cores there, so please program them in parallel. But as I do know, parallel programming is not that simple, right? It requires a lot of complex design of code, for which you have to have multiple exclusion areas of execution. You have to wisely use locks, and you start running into races between the parallel threads, and all this complicates considerably the design of your solution. Okay, so the other problem that started showing up more recently around actually this year is related to the electricity usage of the data centers, right? I mean, as we have more and more cores, the prices for a node in a cluster decreased considerably because there was this large, huge scale market for data centers. And we start having a large and huge actual increase in electricity users in those clusters. Okay, so these graphs demonstrate that. On the x-axis here, of course, you have the year, and here you have a terawatt-hour consumption of electricity in data centers in between 2010 2030. And the forecast that we have for the coming years and are kind of announcing that we are running into big trouble. Okay, what's probably gonna happen if you do everything fine? In other words, if we apply all possible low power optimization techniques, since clock gating at the die level to managing using machine learning techniques, the on and off on nodes in a cluster. In other words, you do everything right, this is gonna be the consumption of electricity in these clusters. So we are starting an area where this is going to grow no matter what. Of course, we are not going to be able to do the best possible solution because there is always possibility for optimization. So the expected growth of the electricity consumption in those clusters is going to be represented here in the red line. And in the worst case, if you do a bad job, this is going to, in the green lights, represent the growth in electricity consumption. So probably what's going to happen is something in between the blue and green lines, but both of them start showing like a close to exponential increase in the electricity consumption. Okay, so we have two problems now. The first one is the parallel program is hard. The second one is that we are starting to see a huge growth in power and electricity consumption. So what can we do to handle those problems? We can go back to our design board and see what we did in the past with the architecture roadmap. In 1947, sorry about that. 1947, we had the first transistor being designed, right? And after that, to keep growing with more transistors and with our ability to do more computing with them, we had to put abstraction layers on top of them. So encapsulate the transistor into logic gates around the 60s, and the projects were done manually, and designs kept the architecture continued to grow larger, and to handle that complexity, encapsulate the logic gates and function units, and then encapsulate around the 70s, and around the 80s, we encapsulate them into processors, actually early 80s, and then we move to multicore for the reasons just mentioned. So what's going to happen next? Now that we have this programmability issue related to parallel computing, and we have this problem with power consumption. So what the industry is forecasting in the long run is to an era that the accelerators will dominate computing. And we have kind of witnessed that already, right? With the GPUs, like for example, the NVIDIA GPUs, the AMD GPUs, and those small Mali ARM GPUs that run cell phones, and there are all other solutions from Apple, Intel, and so on. They're kind of anticipating that this is going to happen, right? Another technology that we have been using for some time now, and which was kind of giving us a glimpse what's going to come in the future, are the vector units, right? The vector extension from Intel, ARM, Intel, and IBM have demonstrated that we are like kind of pushing some computation to some specialized hardware would be a good solution to improve programmability and power consumption. And also the FPGAs, right? They also have played this role of acceleration. So what's going to happen in the era of accelerator is going to be a generalization of that. We're going to start seeing more and more accelerators specialized for the telecom domain, machine learning domain, and so on. So this is just a continuation of what was started with the GPUs and ISA extensions on vector that we witnessed kind of 10 years ago. Okay, I already mentioned about the GPUs, not much to talk here. Actually, they are specialized engines, accelerators for kind of dual loops. If you have a dual loop, so it's a well-behaved loop, which doesn't have lots of loop carrier dependencies, this code is run perfect on GPUs. And we have seen demonstration of that for graphic computing and machine learning and some other workloads. Okay, sorry. Another workload has become extremely important recently resulted from the success of machine learning is tensor processors. So NVIDIA has put forward a solution for that. There is the Apple Neural Engine and also the in-house solutions, TPU solutions from Google. FPGAs also have played an important role, particularly for those workloads that you can pipeline and do very fine-grained computation in areas like telecom. So we have seen interesting solutions from Xilinx and Intel, and because this ability to design a flexible accelerator, companies have, big companies, CPU vendors have witnessed that, the success, and since there was these are important technology for the accelerator area, they basically made decisions to buy these companies. So what I mean by that is that Intel, of course, everybody knows that, bought in Altera, and AMD bought Xilinx. But they did that because very good designs were done with this technology. And it seems to be a core technology for the design of future accelerators. And there is also this movement going on more recently to use the concept of ISA extension and bring these accelerators close to the CPU. So we have seen more and more ISA extensions, and some are anticipated to come in the future. So this, of course, started with the vector extensions in the past, as I just mentioned. But recently, this year, we witnessed design decisions from Intel and IBM, which also goes in this direction. So Intel has released the advanced matrix extension, which is basically a set of assembly instructions that you can provide for this instruction, a pointer in memory for matrix A, a pointer in memory for matrix B, and a pointer in memory for the result matrix. And in a few cycles, you can do a whole matrix block, a block of a matrix multiplication. Also, IBM has released the matrix multiplication assist with their Power 10 architecture. This was released this year, 2022. And this extension is very similar to AMX and does exactly the same. You can have assembly instructions which basically do whole matrix multiplication operations. So we are going to see more and more of these extensions. Those extensions which are very relevant to the workloads run on CPU are going to move closer to the processor. All right, so let's dive into some of these extensions. For example, let's look over the ISA-based accelerators and look how Power 10 MMA is used to accelerate CNN models using faster matrix multiplication. This work was done with IBM, in partnership with IBM Toronto, and it was mostly done by three students at LSC, Victor Ferreira and Rafael Souza. Okay, I'm not going to spend much time here explaining what's a convolution because most of people already know that, but just a quick review of that. You have a filter, and you basically project the filter on top of an input of the convolution, which is typically an image. And then you do multiplication element-wise here, and you accumulate the result into the single center position of the window that you just projected. And this is the result of applying this filter to this window on the input. Okay, speeding up convolution is a very important operation. If you look at the CNN models I have nowadays, at about 40 to sometimes 70% of the computing time is spent doing convolution. And therefore, focusing optimization on convolution is extremely important to this type of workloads. All right, but how this is done in the case of the Power 4 MMA instruction matrix multiplication extension? Basically, what you have is a kernel, which is the filter, and then you have the projected window on top of the input matrix. Of course, your input has a number of channels, but let's focus our attention to a single channel here. So you get the window from the channel, from the projection of kernel on top of it. And this kernel moves, in our case, moving from left to right, top to bottom. So it moves. And after it moves, you get a new projection of the filter, and you do the convolution on this new window. That's the overall work that you have to do. To achieve that, there are two very well-known techniques. You can first do the matrix multiplication use inner products, or you can do it using outer product. In the case of the Power 10 architecture, the MMA extension uses a hardware to implement this matrix multiplication operation, which uses the outer product algorithm. I'm quickly going to explain that. So we have your set of kernels of filters, and you want to multiply the kernel by their corresponding window. And this kernel, for example, is going to move on top of the input, generating windows, and you want to do the multiplication. The first thing you have to do is basically to load the window into the into what we call the vector register. And once you load them, you have to load the second window, and you keep doing that. And then you load the kernel on this other vector register here, and you do the load the other kernels, okay, till we fill in all the set of four of the VSR registers, these four kernels here, and the four windows that correspond to their projections on the input. So you basically load here a VSR with, for example, for this first VSR here, you load them with 4 elements of the windows and of the kernel, sorry, and 4 elements of the windows into the second VSR register here. After loading them, you basically do the outer product. You take one kernel, element K0, and multiply by the corresponding elements on different windows, and you get these two little products here. And you do for K1 as well. K1 multiplies by 2 elements of the window, and you get these 2 other elements here. If you keep doing that, take the kernel elements and multiply them by the window elements, you're going to be able to fill in this whole accumulated matrix here, and you finally obtain your outer product. For that particular set of kernels, for example, the row here corresponds to kernel 0, the other row here corresponds to kernel 1. So you continue doing that for the remaining elements of the kernels of the windows, keep doing the outer product of them, and accumulate on top of this accumulator, which is kind of a hardware inside the MMA unit. And you repeat that for all elements of the kernels, the window, and continue repeating that for all the channels. And when you, at the end, you're going to have, you manage to compute your whole convolution for those kernels and that slice of your input. All right, so in the case of the Power 10 MMA-based architecture, you have a number of accumulators. You don't have one, so your rate should be able to use all the accumulators that you have available. Victor and Rafael did a very good job in terms of that, got very interesting performance, and they're currently writing a paper about that. This is a new algorithm that we are going to explain in the paper. All right, so let's move on to another kind of accelerator. Let's look at the FPGA-based accelerators. In this case here, I'd like to mention the work done by Andrew Putnam at Microsoft on Bing and CNN. All right, so the story goes like this. After graduating from UCSD, Andrew Putnam moved to Microsoft Research, and he was a FPGA person and said, hey, maybe we could use FPGA to accelerate game. So we started talking with people at Microsoft and convinced them that there were some parts of the Bing code that could be done faster in FPGA. So they basically decided to do this small experiment to add a small FPGA board on a typical computer server node. The node has some disks, has the main CPU board here, the CPU. You have two CPUs here, and with some ports, each one of those, and we do have memory slots here. And the idea is to add this little FPGA board here, attach it to the CPU host and to the NIC card, which you could design some accelerator kernels for some parts of the Bing, which is the search engine from Microsoft. Okay, so they did that for one single node and tested out. It worked fine. We could get some speed up. And after that, doing for a single node, they did for a rack and then for a whole cluster. So Microsoft assigned a whole cluster to test out this experiment. And the results that they achieved were this. Basically, on the x-axis here, what you have is normalized latency, the amount of time that takes to do one query at the Bing search engine. And the y-axis here, what you have is queries per second. It's the throughput, number of queries that you can do per second, Bing queries. All right, so they did that with roughly more than 1,500 servers running the FPGA boards on each one of those servers. And with the modified version, which combines software and FPGA for Bing, which is approximately the Bing solution, approximately 30,000 lines of C++ code. Okay, what did they achieve? The blue line here is a software-only solution. Okay, as you can see, as you grow, the latency grows. Number of queries per second grows as well, because it tolerates more latency to do the queries, right? When they added this combined solution of software and FPGA, they found some very symmetric. For example, if you freeze the latency, you bound the latency to a specific value, your software plus FPGA can deliver 2 times increase in the throughput. In other words, by saying I can tolerate latency of 1, normalized latency of 1, you can do more than 2 times the number of queries that you could do before with the software-only solution. Okay, and this opens up space to reducing the servers, because if you are content or happy enough with the normalized throughput, you can basically reduce the numbers of server since now we are doing the queries in much faster way with the support of FPGA. So this opens up to cost reduction. On the other hand, if you are happy with the queries per second that you have on your throughput, from the software solution to the hardware solution, you have a considerable reduction in the latency that you can do per each one of the Bing queries. There was approximately almost 30% latency reduction. And with that, you have more computing time slack to improve the relevance of the query. You can do a more sophisticated query now because you have more time to finish up the query. Overall, they achieved approximately 30% reduction in cost and under 25-watt power envelope, and without any hardware failures. This project was a very good success, and they extended these ideas to deep learning. So for those at that moment at Microsoft, lots of image classifications using CNN under their machine learning cluster operation was being done using Altera FPGAs. And this was, since Microsoft and Intel has this very strong partnership for a number of years, this was, in our opinion, the kind of the design success that kind of induced Intel to move to buying Altera. This is, of course, a personal opinion. Okay, and since we're living in the machine learning, artificial intelligence area, people might ask, oh, hey, how about AI-based accelerators? For that, there are a number of solutions out there. I just would like to bring this one. It's a small company, which is very considerably large. It's called BrainChip. And what BrainChip has, they have this Akida chip. The Akida chip is a very interesting accelerator for machine learning, which I want to give a rough overview next. What the Akida chip has is, what they did, basically, they look at your input. If your input has a number of zeros, it makes no sense to do the convolution on top of that part of the input. So this designed this event-based the convolution mechanism and patented, in which they locate in their hardware which points of the inputs are zero, and they don't do computation on that. They basically move their filters on top of only the elements of the input which are different than zero, and kind of segment that part of the input and do the convolution only on those. In other words, they locate these areas where the input is different than zero and have some interesting event-based hardware to dispatch the convolution to compute only on those regions. The nice thing about this is that the result of convolution is a set of small tensors, which you can move to the next layer of convolution without needing to compute the whole input. In other words, this event-based idea kind of move your slices of your convolution input forward across the all layers of your machine learning model, and considerably reducing the amount of computation that I have to do, and more than that, considerably reducing the power that we should to do that. Okay, so what are the numbers for the BrainChip? For example, if you take the mobile net model, if you do that, for example, with a nano NVIDIA GPU at close to 1 gigahertz, you're gonna get approximately like close to 3,000 milliwatts of power consumption. Okay, but doing that with their chip, you can have a kind of close to one third of the clock rate for the same tech node at 28 nanometers, and you can extract for the same model, you're going to consume only 46 milliwatts. So this is a very, very interesting reduction in power consumption, and which kind of highlights the relevance of accelerators in this new era. All right, let's talk a little bit more about this partnership which is going on with Xilinx. We have a number of people working here. We have Elisa, we have also Pedro working on this project, and Lucas. And the idea of this project, which has been supported with a partnership with people from USP and University Federal of ABC, is to accelerate computation, particularly stencil computation using OpenP. We have already done one design point on that. We create a new OpenP plugin for FPGAs and LLVM, and test that in this small cluster, which had 6 nodes connected using fiber optics. As you can see, these are the nodes. This is a fiber optics connection, and each one of these nodes has a VC709 board from Xilinx. So how does this thing work? Basically, what I want to do is being able to do hardware computation and more than one node. In other words, we don't want to constrain our hardware kernels to as a single node. And the idea is to use the OpenP cluster, which also being developed at Unicamp, in our group here, to enable that. So for example, take the Laplace stencil operator. What you want to do is push some data into it, say for example, a grid of some problems like emergency seismic analysis. And this one being able to use some internal switch on the hardware and push this through all this Laplace stencil element processors. And for to be able to go beyond a single node, you should be able to communicate that through the fiber optics, do the same traversal on the Laplace stencil elementary processors, and then go back to the other board on the other node and communicate the results to the host. So the idea is to do that in a whole cluster, okay? And this is a very interesting work, has produced some very interesting preliminary results. As you can see here from Laplace 2D solution, each one of these curves here with different colors correspond to the number of the size of the grid that you're working on, on the x-axis here, what you have is the number of IPs that you have for each one of those boards. Okay, and if you're talking about 4 IPs, as we grow the number of IPs, we have a very interesting, close to linear growth in the gigaflops performance of this solution. Also, this approach also scales if you scale with the number of FPGAs. Okay, the number here of IPs correspond to that IPs inside a single FPGA. On the right side here, if you grow the number of FPGAs and for some different solutions ranging from Laplace 2D to diffusion 3D, you also get a very interesting close to linear speed up. So these preliminary numbers suggest to us that this are very has a very potential possibilities, and we are pursuing this project further with new Alveo technology in a joint partnership with Xilinx. So from the programming perspective, how does this work? I don't go much into the details here, but you can consider that with this 4 here, you are basically designing a pipeline, a set of calls to the Laplace 2D, okay? And I'm passing a vector to it to do the computation. This vector is a linearized form of a small mesh. So I'm creating this pipeline and calling this function Laplace 2D. And the nice thing about OpenP, it enables you to give a different execution for this code here. But using the variant here, clause from OpenP, you can basically say, hey, every time you execute the do Laplace 2D function, every time you call it, if I specify the command line that I want to use the device as the VC709, this architecture, please call the Laplace 2D, this other option of Laplace 2D, which has hardware in front of it. In other words, at execution time, or compile time, sorry, you can basically say, hey, if when I want to run this, and I'm using a hardware accelerator, and I want for you to call this different variant function to do the execution for that function. This is very good because it enables us to first test our solution in software and then move the accelerator quite smoothly. All right, but as you can see, I talk a lot about different types of accelerators, right? I talk about GPUs that you already know, about vector extensions that most of people understand those. And you're seeing more different accelerators. Accelerators from FPGA front, accelerators as more sophisticated accelerators like the matrix multiplication for the AMX and MMA technology. Soon we are going to see more and more of these CPU-tight coupled accelerators for other domains like telecom and so on. But the one point that remains is, hey, I have this huge code base which is already being developed there. How do I capture fragments of code that I can easily compile to these accelerators? And we have some projects going on here at UNICAP on that. And the first one that I'd like to describe is the one based on the Gemini accelerator. The Gemini accelerator is a machine learning hardware accelerator attached to a Rocket RISC-V processor, which enables to do very fast generic matrix multiplication and some other linear algebra operations like dot product. And it has also some piece of hardware that enable to execute some important operators for machine learning, like ReLU and so on. Overall, what happens is that data is brought, for example, from the also cache through a DMA engine, and then the data is put on these raster banks here, and then you push those raster banks through a systolic array, and you can do your multiply accumulation, your gem, your dot operation, and which are basically kind of background blocks for convolution and other linear algebra machine learning operations. All right, so what we did with the Gemini, what we did basically is trying to use Gemini, we need to find pieces of code that are amenable, that you can use to accelerate the computation. But how do you find the code for acceleration? Say, for example, you have like 1 million lines of code, and you want to find, locate, which are those fragments, which, for example, we can use to do a very fast matrix multiplication. All right, what you want to do after locating that, those code fragments, is to substitute the execution by a little C wrapper around the hardware instruction, or a set of hardware instructions, which offload the computation data to the accelerator and then runs that operation, say, for example, matrix multiplication. Okay, to do that, there is this very interesting project going on here at UNICAP called source matching and rewriting, which is being developed by Vinicius and Luciano. What they basically did, sorry about that again, what they basically did, they designed this interesting pattern replacement length, right? You specify that you want to design a pattern. You see here, for example, a dot product, and you say, hey, every time you find this pattern in a source code, please substitute it by this other code fragment here, which basically calls the Gemini single precision dot product. So by doing that, you would be able to locate in a large code base dot product operations and then call the accelerator to accelerate those. This saves the users a lot of time, right? Because otherwise, there are many ways to, you have to go through this whole code base, look for that, and substitute by the acceleration operation. And now, you don't need to go into those details. You don't need to go into details on how do I call the accelerator, how do I handle the DMA there. Everything is encapsulated inside this Gemini S product, and you could also design Gemini variations for each one of those interesting BLAST calls that we have in typical linear algebra libraries, right? And making this a very standard way to call the accelerators for those operations. Okay, but how does the source matching and write toolchain works? It's quite simple. You basically specify your fragment that you want to detect and the replacement, and then you generate those in a set of patterns. And we have this technology which converts these patterns takes the patterns and build their data dependence graphs and control dependence graphs, and encapsulate those into what you call a pattern finite automata. So this automata basically kind of factors all the patterns into a single automaton. In other words, similar programs, similar patterns have similar DDGs and CFGs. So in this sense, the automata kind of take the commonalities between these patterns and encapsulate them, compact in a very interesting way. And this PFA can be thought as a library. So with this library at hand, with a set of patterns specialized, for example, for the other product, you can take your generic source code input, pass it through the MLIR compiler, and have SMR read the automaton and then detect those patterns inside your code, the source code. If the patterns detect, you substitute it by its replacement, and then you move on downstream through the algorithm compiler and generate unified binary code. But does this produce interesting results? It does indeed. For example, for the generic matrix multiplication, if you take a matrix and use this technology, SMR technology, to do the replacement, you can get very interesting speed up. On the right side here, you see a graph where on the x-axis is the size of the matrix that is doing the multiplication, and speed up at the y-axis for the simple precision jam. As you can see, for a small matrix size, the whole matrix fits into the Gemini accelerators memory bands, and you achieve very large speed ups. On the other hand, as the size of the matrix grows, the whole matrix doesn't fit inside the engine, and you have to do tiling. And because you're doing tiling, you're basically reduce the speed up that you can achieve. But still, you can achieve speed ups of the order 20 times. This was done generating code from using the MLIL, the Amplitude chain, as I mentioned, and simulating the Gemini accelerator using Verilator. And one important point here is that the baseline for this is optimized open BLAS. As some of you probably know, the BLAS technology leverage on the go-to algorithm, which tries to improve the tiling of the matrix across the memory hierarchy. In other words, the baseline is already an optimized matrix multiplication algorithm. All right. As a conclusion, I would like to say that there are accelerators. The accelerator area is starting. Okay, it has been slowly progressing, and it's going to grow for a new area in computer architecture. In other words, the architecture is not dead. Long live the architecture. And I work together with a colleague of us here at UNICAMP called Lucas Banner in this IEEE micro compiler for accelerator special issue, which was released by IEEE micro this past August. So feel free to go there and look at the papers. They give a rough and overall picture of the current state of code generation for those accelerators. All right, thank you very much, and I'm open for your questions.
Okay, thanks, Guido, for the excellent presentation. Let's open up to questions. Does anyone have a question? Oh,
yes, thank you. Hi, Guido. Thank you very much for the presentation. It was very nice. My question is about software. So what do you think those hardware evolution will mean for the development of application? I mean, in the sense of programming language in the future.
Yeah, thanks for the question, Yvette. From my perspective, we're going to have this transition phase, right, in which we are going to have all this code base there, and approaches like XMR will have to, or others, of course, will have to help in this transition phase, okay, in which we capture these code fragments and move them to the accelerators. But in the long run, it might be that design, specialized design language, okay, or domain-specific language like DSL will take off, right? So people will start writing code specific for their domain in a language which already captures those specialized code fragments and do a very good job into moving those code fragments to the accelerator. Okay, so I can envisage like domain-specific languages growing kind of very relevant in the future years. And we have already seen that, right? If you look at PyTorch and some other tool chains, they are very specialized for machine learning. So it might be that, of course, depending on the demand, that you have similar things for telecom domain and some other domains. So in this sense, this might become an area which resembles like embedded systems, where you have those specialized language for specialized solutions. So this one thing on the software side that I anticipate might happen in the future.
Thank you.
Thanks. Someone else? Rodrigo?
Okay, I have one question. Can you please show that graph about power consumption on computer clusters?
Just a second, okay.
Okay, so my question is, if this increase in power consumption,
this is actually electricity usage, right? Terawatt per hour. Okay. But anyway,
yes, terawatt. Okay, so this means that we have larger clusters with consuming more power overall, but still in this trend, the computing is actually getting more efficient, right? We're still getting more watts.
That's true.
Yes, and I do see that, I don't know, I think that accelerators are more friendly on power consumption overall, and we have a limit on how we can scale the frequency on a chip, so we rely on more computing devices. But my question is, wasn't this is power consumption, is it going to be solved by these new architectures? Because the trend overall is that it's still going to grow. Even if we get more efficient, we're still building more computers and trying to utilize more computing powers.
Okay, yeah, I see your point. I mean, these are two orthogonal things, right? One thing is a node being more efficient. The other thing, you're going to need more nodes, right?
Yes, exactly.
So, and they're not related, right? Because you're going to have more and more users of more and more applications. Of course, you're going to need more and more nodes, right? But the one thing that I learned along my career is that you mentioned earlier in the questions, is this problem going to be solved? No, problems are never solved. Okay, never. they tend only to continue growing complexity, and the engineers running after them. So of course, this is not going to be solved. Okay, but what you can do to minimize it is to by using accelerators, it's a technology that definitely can minimize that. I don't have the plot here, but there's this nice, interesting graph which shows the amount of power consumption that it have using just pure software on CPU, or using an FPGA, or use an ASIC dedicated for the same function, right? This is very old knowledge. People know that putting things in hardware makes a drastic reduction in power consumption, because you don't need to move data around as you have to do in CPU. You don't need to load caches, okay, and you don't need to do page faults to go around. If you manage to have very good on-chip memory, like for example, some of these AI accelerators have 16 megabytes of on-chip memory, and if you do a smart kind of way, in a smart way, you move data from off-chip memory to on-chip memory, and you keep the computation inside the chip, you can considerably reduce power consumption, because the rest of the computation, like for example, doing matrix multiplication, it's not going to hit cache misses. It's not going to hit page faults. It's not going to use TLB, right? So there are lots of things associated with execution software which burns a lot of power just for bookkeeping, okay? Bookkeeping of the computation. So if you can manage to smartly move data on-chip SRAM and do the computation hardware, all this bookkeeping of your code, right, instruction caches, etc., are gone. And okay, that's the good news. We can consider, if you do smart designs in terms of accelerators, you can push them to nodes, can considerably reduce their power consumption. But yes, you're right. On the other hand, people are going to continue using more and more applications. We're going to have larger cluster. But what we want to do is to push this curve down to the blue one, right? Because if we don't do that with accelerator, you might end up hitting the green curve up there, which is the worst case scenario.
Okay, I see that we can, and I know the idea is to push the wall forward so we can still leverage more computation. It's not that much related, but still in this graph, we are seeing the total power consumption over a year, or is this the maximum consumption of the cluster if it's fully utilized?
Yeah, this is the electricity usage of a data center.
Okay, so it's the measured consumption.
Yes.
Okay, one last thing is just that we have a lot of computing devices. We can have specialized hardware, as you said, and try to not waste power moving data or, I don't know, doing bad things with the memory that is cached. But I have the impression that it's hard to fully utilize this. And I think we waste a lot of energy with idle computers or even idle resources, idle cores or idle accelerators during an execution. Are applications, I don't know, occupying all those resources at the same time? Is the utilization rate of the system overall high?
I'm not sure if I understand your question, but okay, I will answer. Okay. If you're running an application on using an accelerator, I mean, you cannot share it with other applications, right? I mean, you have to do context switching, go to another process and use it. Okay, so you have to rely on the operating system to do that. Okay. Regarding the overall utilization for the whole cluster, there are a bunch of people working on algorithms for that. For example, Sandro had in the past a student who did a lot of interesting work on that. He's going to work at Meta, right? To find how do you do a better utilization of the cluster node. So you might want to look at their papers. Questions?
Okay. Someone else? Gustavo.
I have a question. Thanks for your presentation, Guido. It was very insightful. My question is about specifically about the machine learning accelerators. So we're witnessing basically an explosion of the number of accelerators, but at the end they're all trying to do the same thing, which is accelerate machine learning workloads. Do you think that in the future we're going to see like those manufacturers merging and we end up with a single or two products from two competitors? Because it seems to me that there are many players and they're all trying to solve the same problem, and at the end we know from history that usually one or two winners are left in the competition. Do you think that that's going to happen?
That's a great question, Gustavo. Very good, thanks. Yes and no. Okay, I'll explain my answer. Let's compare with a similar scenario you have today in computing, right? We tend to believe that computing is just this computation of these huge data centers, okay? But there's a lot of computing going on the embedded system area, right? If you look at the computation happening on data centers, they are very regular. The solutions are classic solutions. You have like CPUs with GPUs attached to them, and we're doing one type of workload there, which is basically training for machine learning, right? The other type of workload you're doing that is like search engines and recommendation engines and so on. So on the data center side, for those type of workloads, everything is very homogeneous in the sense that we have like have a CPU, a GPU, running there. Okay, but if you look at the closer to the edge, close to the embedded system area, you look at you're gonna see more fragmented solution. You don't see a single player there. You have lots of different players, right? You have those small boards which do like video processing on cameras. You have small processors doing some kind of modulation, the modulation in digital domain on base station for cell phones. So on the embedded domain, you don't have a single player, right? You have ARM, you have RISC, you have those specialized MIPS processor. So on the other type of workload close to the edge, when you say close to the edge, close to the end user, close to the sensor, you have this huge market that is not uniform. Okay.
Okay.
All the hardware accelerators that we are seeing are more on the inference side of machine learning on the edge. Okay.
Okay.
It doesn't seem to me that you're going to see a single player, because some people want to combine, for example, natural language processing with machine learning. Other people want to combine video segmentation and computer vision with machine learning. Other people want to combine some other domains with machine learning. And this will bring like the accelerators might be a kind of a small block which is gonna be surrounded by other hardware to those specific domains. Okay. So in this sense, I don't see a single player on this area of inference on the edge. On the other hand, on the side of the cluster side for training, it might be possible that this happen. It might be that some of these companies achieve a very good success in to have tensor extensions to their CPUs, like for example, traditional CPU vendors like Intel, IBM, and so on. And that some other, even NVIDIA comes with some very specialized hardware which is more efficient to do machine learning, right? Because as we can see, if you have the right amount of silicon, the same amount of silicon, you try to run the models using GPU or using some accelerator, the accelerators are going to gain at the end. So it might be that NVIDIA moves, and or of course some other players have in-house solutions like TPUs in Google, they already have that, move to use specialized hardware for machine learning. So you're going to see, instead of having to see a GPU which has been kind of changed a little bit to do tensor operations for convolution, so on, it might be that NVIDIA comes with a specialized GPU for doing machine learning operators. Okay, so this kind of homogeneous and single solution is going to probably happen. Okay, on the data center side of the market, but on the edge, I don't think this is going to happen.
Okay, that's a great answer. I was thinking about like the data center, but I didn't look at the other half of the market, which is the edge.
And it's actually not going to become the half of the market, because with this 5G technology, which enables a very good bandwidth between sensors and the cloud, this market is going to grow considerably large in the years to come.
Yes. So and I think adding to your answer, only a few key players have the computing power to train these networks, but everybody has the power to do inference on them, but not training.
Exactly. Absolutely. Yeah. And the holy grail of this is doing training on the edge, right? So people are trying to see if they could do parts of the training on the edge and parts of the training in the cloud. There's already some technology being thought maybe could do a sort of a little incremental training on the edge, and they kind of have workload for the training be done in the cluster, and this thing talk to each other.
Okay, yeah, that will be interesting.
Okay. No more questions. So let's thank Guido for the presentation.
Thanks, folks. Take care.